out and made a plan for doing ground. What are the necessary things that is to do LLM development from scratch. So we'll first start with a cluster check, or the things that are involved more from the hardware perspective. Like when you're many a times we see that when you're going to train a model, you do not have a crystal clear idea about like what is the expected performance in terms of computation or communication you're supposed to get when you're going to run your training job or inference job. So we need to understand a bit about hardware, like what is the performance on multiple GPUs, ensure that your that are training or inference performance aligns with the hardware benchmarks and so on. So today in this session, we are going to cover this particular part so that you are ready to interact with the cluster or the nodes or GPUs that you currently have, and then you have a clear idea, some clarity about like what is the actual performance that we have from the hardware and what is the expectation that we can get during training. Then in the second session, we are going to start with the data curation, because data forms a very important part of LLM training. So we will see like what are the different aspects of data curation, what are different stages that we do, and also going to cover like the part of mixed precision training, because we in HPC kind of thing where we use 4 bytes or 32 bits floating point for training precision for storing weights. Here we are going to have a mixed precision training where gradients are stored in a different weights, different bits, and weights are stored in a different bits, and optimizer is different, and so on. In third session, we are going to cover how do we do distributed and scalable LLM training on a large scale cluster, because we know that we have large number of parameters that needs to be trained, and there are large number of tokens on which, or the data input data on which parameters are going to be learning. So there are like different parallelism techniques that allows us to parallelize the different data points, or parallelize a whole very big model onto different GPUs, onto different nodes separately. We'll see that what are those parallelism techniques, cover the frameworks and wrappers that allows us to do these parallelizations efficiently. And then we are going to cover what are the recipes and best practices to do this distributed training, large LLM training on a very large cluster. Then we are going to cover the post-training and evaluation, which forms alignment part of the LLM. Like once you're trained, you need to ensure that the output that is generated from the LLM aligns with the human preference and so on. And evaluation also forms a very important part. And then at the last, we are going to cover deployment. How do we do efficient, once we have developed the model, how do we efficiently deploy it such that we maximize our throughput, reduce our latency when the large number of the users are going to use that model. So there are different aspects like batching the input requests. Then we have to do state management, because we are going to do a multi-turn conversation like ChatGPT. We do multiple conversations with that, so we have to manage states, and then we have to manage inference servers as well. So there are different aspects in deployment that we are going to cover. So these forms kind of 5 sessions where we are going to go into a deep dive and also do a hands-on, particularly hands-on in the sense like I'm going to show you on my cluster or on my GPUs. We do not have a setup for you to all to test at this point of time, but you can take those notebooks or tutorials and do it at your own infrastructure by yourself. So yeah, let's get started with the first session. Here, I'll start with this particular important diagram, I think, which most of you have some idea about. Like there are 2 aspects in a GPU or in any computing. One is computation, and the other is communication. So there are different cores in a particular CPU or GPU that communicate with each other. There are GPUs which communicate with other GPUs within the same server, and there are servers who are communicating with other GPUs in another server. So communication forms a very important part in LLM training, because when we do large scale training, like when it involves more than one GPU, and it usually when we go from, let's say, more than 2 billion or 3 billion parameter, we need to have multiple GPUs to be allocated during the training workload. So there is a communication aspect which is generally measured in gigabits per second, and then there is a computation aspect which tells you like how many number of operations a particular GPU type or a model can process in a second. So we generally measure now in teraflops. So it's 10 to the power 12 flops per second. How many can it be done theoretically by the particular GPU model? And both of these are in sync, and they form the important backbone of when you are going to train or inference your workload. So then you will receive your effective performance based on these computation and the combination. And generally, communication forms a certain bottleneck, which different GPU vendors are trying to alleviate and reduce this to ensure that you reach the highest effective performance. And these, both in training and inference, we measure in terms of tokens per second per GPU during training, and during inference we measure like there is an inter-token latency, like how much is the latency between generation of two tokens during decoding phase and so on. So yeah, this is the overall motivation of why you should learn about these sessions, why you should attend these sessions, basically to understand all these, both these parts like computation and communication. That's what we are going to cover today. And we are going to touch a bit upon the how to measure the performance also, as well in this session. So yeah, that forms the basic motivation of why we should learn about these, the underlying hardware, and understand it to get the clarity about when we are going to run the actual workloads, and it should align with the hardware. Yeah. Now, we know we mostly do multi-GPU computing now because, and there are certain libraries like NCCL. So NCCL we generally pronounce as nickel, which is a library providing inter-GPU communication primitives that are topology aware, because when we are going to look at our complete server, there are multiple GPUs, and these multiple GPUs communicate to other GPUs, to CPU, to NIC, that is network interface cards, and via network interface cards to another server through there is some topology which should be pre-told, which should be understood when we are going to run our workloads. So NCCL or nickel library helps us in easily integrating these topologies, these inter-GPU communication primitives into our applications. And there are like few core operations that happens during large-scale distributed deep learning. There are all reduce, all gather, reduce, scatter, and so on. And then there are communication that happens over these interconnects. So one is PCI server, which is very popular way of communicating from one component to another component through PCI lanes. And then there are like NVLink that sits within the DGX or HGX systems. So the system that C-DAC has is kind of a DGX and HGX systems that communicates from one GPU to another within a server through a NVLink. So NVLink is part of the inter-GPU communication network, and now recent systems like GP200 and NVL72 has also communication from one GPU to very large set of GPUs through NVLink itself. So NVLink is a fast communication network that helps us in reducing these communication bottlenecks. And yeah, and these kind of interconnects dynamically detects and use the fastest available pattern or platform. So yeah, these are the 5 things that we are going to cover. How does multi-GPU computing happens in deep learning? What are the hardware and the performance? Then we are going to see the real world performance through MLPerf benchmarks. And then from the computation part, we are going to see HPL libraries to get the effective performance in terms of teraflops or gigaflops per second. So yeah, let's get started with the multi-GPU computing. So when we are training a model, if it is not going to fit within a GPU RAM, so for example, if you have a model, let's say, which is of 5 billion parameter, and then you are going to train it over, let's say, 100 billion tokens. So now this particular model is not going to fit all the parameters that are required or all the components that are required to train the model into a single GPU. So there are like different paradigms that helps us in alleviating this problem. So one is data parallelism. So data parallelism is like when you split your model. So if your model is going to fit within a GPU, then you split the model across different GPUs so that your the training time reduces by leveraging all the GPUs within your network. Then there is a tensor parallelism, pipeline, and expert parallelism, which are for cases when it does not fit within a GPU. So in tensor parallelism, we split the tensors across different GPUs or across different nodes. So across different GPUs, not nodes. So tensor is like when you have like a complete matrix A, then you are going to split the matrix into A0 into subset of A1, let's say some smaller part of bigger matrix, then some other part of the matrix is processed onto some other GPU server or GPU. And when these operations happen in parallel, so you are going to accumulate or aggregate all the computation and then broadcast the computation to all the servers, all the GPUs within a server. So this is a tensor parallelism where these 4 operations are involved. So these 4 operations we are going to see in the subsequent slides. And then there is a pipeline parallelism where you are going to squash or split your complete network into different splits. So let's say if you have a 10-layer network, then 2 layers resides in GPU 1, 2 layers resides in GPU 2, and so on. So now you have to wait for one layer to finish and give the output to the next layer. So that's kind of a pipeline. And there are a lot of send and receive because we are going to pass or broadcast our inputs or outputs to the different GPUs to ensure that all of them are in sync. And then there are recent expert parallelism for mixture of experts kind of network, where we are going to move all our experts into an all-to-all operation that we are going to see. I think this might confuse things. But yeah, just to give you a broad idea, here are the different techniques that are involved when we are going to do this multi-GPU computing in deep learning kind of application, deep learning kind of paradigms. So yeah, I'll start with some basic communication primitives that are very much involved during the GPU operations when we are doing this training and inference. So one is this particular reduce scatter operations. So this particular reduce scatter operations is useful when during large scale training when model gradients are split among GPUs. So each GPU reduces or sums its assigned piece of gradients. Yeah, so each GPU reduces its assigned piece of gradient. So let's say there are these 4 GPUs, and then each GPU has these 4 sets of data with them. And so now when these model gradients, these are like model gradients, these are split among GPUs, right? So you need to reduce this. So you have to aggregate it once to ensure that all of them are synced after a certain piece of operation, right? Or certain piece of training. So now each GPU reduces its assigned piece of gradients, and then with others, and then only stores its piece. So I'll just run an animation again. So now if you see all these piece of gradients are then, is propagated to all the other GPUs. So this particular part of the data, and then this particular GPU only stores its piece. So this saves like memory and communication, because now it is possible to train bigger models without every GPU needing a copy of everything, right? So GPU 0 only needs to store a copy of one part of the data, not every part of the data. And this is very primitive operation, core operation in the during the communication cycle of the training. So there's a reduce scatter operation. The second operation is all gather. So this is an all gather operation, which is kind of a broadcast operation. So when a model parameters are sharded across GPUs, so like these are sharded across GPUs for efficiency. So before a computation that needs the full layer, because when we are doing a forward pass, we need to have all the gradients or all the parameters in sync. And all gather step basically collects all the parameter shards so that every GPU can proceed with its processing of the forward pass. So this is particularly well used in data parallel and tensor parallel training setups, this particular operation. And so this is kind of a broadcast operation which broadcasts its piece to all the GPUs within its network topology. So you can put all the questions in the chat box, and I'll ensure that after one part is finished, I'll take a look at the chat box. Now coming to the third operation, which is a combination of both these reduce scatter and all gather, which we call as all reduce. Now in a data parallelism setup where each GPU is processing its own mini batch and computes a set of gradients. So remember I told you about data parallelism setting where you have a copy of model being copied across all the GPUs within your network topology. So now each GPU processes its own mini batch and computes a set of gradients. And now to ensure that the parameters are updated identically on every GPU, these gradients must be summed across all GPUs before updating, right? Because once the complete forward pass or a backward pass is finished, we need to ensure that all the gradients are averaged, or whatever operation you're going to do for collecting all the gradients. These gradients must be in sync to ensure that before going with the next set of training step. So this all reduce performs the sum where every GPU, I'll just play the animation again, where every GPU sends out its gradients. They are summed up collectively, and the result is sent back. So every GPU gets the final combined gradients, right? So every GPU sends out its part of the gradient. So this particular GPU has processed its mini batch 1, this has mini batch 2, mini batch 3, and so on. So every GPU sends out its gradients. They are summed up collectively by averaging operation or whatever other operation that you want to do. And the result is then sent back so that every GPU is now has final gradient or the combined gradient or aggregate overview of the complete cycle. So in frameworks like PyTorch, this is managed by libraries like Nickel. So we started with Nickel. We gave this motivation like, why do you have this understanding of the complete topology of your cluster network? And then these are the core operations that forms the background or backbone of the complete large-scale distributed training of LLMs or any deep learning model. So all of this is managed by libraries because these are all wrappers that goes on behind. So we don't know, like when we start with torch.run or when you do model.train, we don't know like what is happening because this Nickel libraries on NVIDIA GPUs optimize this all reduce to minimize communication overhead using some topology of the cluster. Right? So we are going to go into the what does topology of the cluster means and how does this particular GPU 0 is communicating to GPU 1 and GPU 2, so on. How does this happen within the Nickel library? So I hope these core operations, you have got some understanding about it. And there is final all-to-all operations that is prominently used for mixture of experts kind of model, which is more a communication-intensive pattern where each GPU, so I'll just play the animation again. So each GPU has a unique piece of data for every other GPU, right? So this particular GPU has unique data, we know via colors, and for every other GPU. So these are all unique. Now here, every GPU sends and receives a separate piece than all other GPUs, and the results on each GPU are not globally summed. Because right now in the all reduce, we saw that we do the summation or averaging operation and then communicate to all of the GPUs within my network. But here the results on GPU are not globally summed, so that's why it's a more communication intensive paradigm. And data are flexibly exchanged so that each GPU ends up with a different set of data from different sources. And this is required for expert parallelism where different inputs might need to reach specific experts on different GPUs, right? So different inputs. So, in the mixture of experts, there are certain set of experts in the feed forward layer where now we are in expert parallelism, we are going to split the experts across different GPUs. So now in this kind of setting, you don't need all reduce operation because now you're going to communicate only your part to all the, not globally, but to other GPUs so that it can process the different set of experts now. Yeah, so these are the core kind of operations, and now we are going to look at the topology part. So, yeah, I hope I won't find. Yeah. So now this is a topology which you can also check of your server or a server by using this command. We know NVIDIA SMI is the popular way to check what are the GPUs, how many GPU RAM I have, what is the GPU utilization, and so on. So now with the additional topo -m argument, you can see like how your GPUs are connected to other network interfaces or other interfaces within your server. So now this is the topology of A100 system. Now each GPU, if you see, is equipped with 12 NVLink third generation with, and this NVLink third generation has a bidirectional bandwidth of 50 Gbps, so 50 gigabytes per second. Now, if you see so each GPU has 12 NVLinks. Now these GPUs, these NVLinks are all connected through NV switches. So each GPU is not connected through other GPU by a set of wires directly. Instead, there is a intermediate NV switch, which are kind of switching specialized switch chips designed to provide like full bandwidth and all-to-all GPU communication. So NV switches acts as a crossbar switch, not simple pass-through. So this kind of a router in the internet terminology, which transfers the packets from whichever router, and it has the complete understanding of the topology of the global topology. So now this particular NV switch allows GPU to communicate with any other GPU at a full NVLink speed. Right, so these are like my network interface cards, 12 network interface cards. So they are connected from GPU to network interface cards through a PCI lane, and PCI bridges has a lesser bandwidth than NVLink. So we'll see like what are these bandwidths and their scale. But this is how you can get the topology. And now for HN rates, we now have, instead of 12 NVLinks, we have NVLink 18 NVLinks, which are of NVLink 4th generation. So these are like 4th generation NVLinks. And then for B200, which are the Blackwell systems, there is again 5th generation NVLink, and there are 18 NVLinks connecting from one GPU to NV switch, and then from NV switch to other GPU, and so on. So now coming to the point, like we are talking about NVLink too much. So what are these NVLinks? So these, unlike traditional PCI interconnects, which quickly became a bottleneck in multi-GPU systems, NVLink provides higher bandwidth and lower latency. And in like NVLink 5.0 generation for Blackwell systems, we can get up to 1.8 terabytes per second bidirectional bandwidth using these NVLink, 18 NVLinks. So each GPU talk to each other via NV switch, which improves the speed of data transfer and removes the bottleneck that is involved in exchanging from one GPU to another. So there is no bottleneck bandwidth that reduces the latency or affects the throughput of the communication. Now, NVLink also allows the pooling of memory. So all attached GPUs can see and use these are high bandwidth interconnects. So you can see the whole memory space as a virtual pool of memory, which is a very large effective combined memory space. So for example, two GPUs with like, let's say 80 GB memory, when linked by NVLink, can be programmed to act like a unified 160 GB pool. Right? So this is kind of a virtual abstraction due to this high-speed interconnect. So NV switch enables all-to-all GPU communication by interconnecting multiple NVLinks. So this is the particular technology that is used within NVIDIA GPUs to ensure high GPU to GPU or CPU to GPU bandwidth communication. Now, when we are talking about these core operations, we highlighted or mentioned about the topologies, like how GPU 0 is going to communicate with GPU 1, 1 to 2, and so on. So there are two different kind of algorithms that exist within this nickel libraries to ensure that the communication between these GPUs happens seamlessly. So there is one is ring algorithm. So ring algorithm, I'll just play the animation. So let's say there is GPU 0 here, and there are 4 batches of data within each GPU to be going as an input. Now, so ring algorithm, each device splits its data into n chunks. So there are n devices here, and in each step, every device sends one chunk to its neighbor and receives a chunk from another neighbor. So this repeats for n-1 rounds. So every device in the end ends up with a distinct chunk of the reduced data, right? So you can see like all the data within the. So this is more of a step-by-step communication where data is going from GPU 0 to GPU 1, GPU 1 to 2. So you'll need like n-1 passes to ensure that all the GPUs has all the data for like all gather kind of operations, like the broadcast kind of operations. Yeah. And then this is mostly useful in the cases where you have a smaller topology, smaller number of clusters, generally less than 32. So you can, afford to have this one-by-one or step-by-step communication across different nodes. So I mean nodes. Like if you're less than 32 nodes within your cluster, this is a good strategy, or the de facto strategy to do the communication. Now there is another algorithm, which is a tree algorithm, and all reduce and all gather kind of operations to use this kind of algorithm. Now what happens in this is, so data is aggregated or distributed in the following steps. In each round, the number of devices involved doubles. So there is kind of a tree structure here. So let's say my 0 is the root of the tree, and then I have 2 nodes. So it's kind of a binary tree. So all nodes can have only 2 children. So what happens is, for reductions, data is sent up towards the root, combining at each step. And for gathering, complete data is pushed down to all leaves. So it is used when we need to minimize the number of communication steps within our whole system. So this is when the communication steps are more critical than bandwidth, then we use this kind of tree algorithm kind of setup. So this kind of a binary tree of the whole topology of the whole all GPUs in my particular in the whole cluster, and then it tries to communicate with them step by step. I'll just play the animation again. So if you see, there are 2 trees here, tree 1 and tree 2, so blue and green, blue and red. Now all the data from the particular for the reduction step, data is sent up towards from the leaves. It is sent towards the root and is combined at each step. So all the intermediate nodes will have the understanding of, or have seen all the data from the leaf of the whole tree, leaf of their nodes. So these are like 2 different topologies that I just want to highlight, because we want to touch upon like 3 things. One is topology, how my system, the particular server, how other servers within my cluster are connected, and how they communicate through each other using these operations, and how the Nickel library gets understanding of the topologies to ensure that the library can communicate effectively to other GPUs in a shortest number of steps. Now, the third point is, what is the effective bandwidth that is present in both the inter-node communication. So this is inter-node when we have multiple nodes, and intra-node communication when GPU is communicating to other GPU within a node. Okay, so as I mentioned, we are discussing this NVLink all the time till date, till this point of the presentation. Now this NVLink 3, which is present in A100s, we saw that there are 12 NVLinks which are present from one GPU to the NV switch. So each NVLink 3 has an effective bandwidth of 25 Gbps. So 12 of them becomes like 12 into 25, which becomes 300. So there is effective or theoretical bandwidth of 300 gigabytes per second bidirectional communication for A100 NVLink 3 generation. Now, if you come from NVLink 3 to NVLink 4, you have effective bandwidth of around like, I think 400 Gbps, because of there are 18 NVLinks that are present. And maybe my numbers are wrong here. I think there are 600 Gbps, which is effective bandwidth, because there are 18 of them, and each has a bidirectional bandwidth of 50 Gbps. So 18 into 50 comes out to be 900. So single direction, it comes out to be 450. Yeah. And then we have NVLink Sharp, which is again a protocol which allows the different GPUs to communicate through each other directly without having an intermediate passing of data packets from GPU to CPU. So this particular, so let's say if you're communicating from GPU 0 to GPU 1, now the communication happens such that your data should pass to the GPU, because we are doing these core operations, all reduce, all gather, reduce, scatter, and so on. So now, to ensure that the communication goes from one GPU to another seamlessly without having an intermediaries. So, or we can do this reduce or summing operation within using this Sharp kind of paradigm within the NVLink itself. Now we have like NVLink 5, which is present in V200s and so on. So this is about intra-node communication. And for inter-node communication, we have NVIDIA supports like InfiniBand kind of communication network. And there is other Ethernet-based communication network, which is very popular, and we see all together all over in internet. Now, we have a lesser amount of bandwidth than NVLink because we are doing like operating over some copper wires or optical fibers, and this has effectively lesser bandwidth, and we can possibly do it within a single server. So this has particularly, so let's say our system TGX 800 has like 200 gigabits, 8 ports within to communicate from one node to another, one server to another, and that gives you an effective bandwidth of around like 192, but the theoretical bandwidth comes out to be around 200. So each if you multiply like 200 into 18, 200 into 8, which is 1600 bits, which comes out to be 200 bytes, right? So we generally communicate in bytes now, but here the Ethernet or InfiniBand kind of networks report them in bits. So you should be aware of like if it's a capital B or a small b. So here it's a small b, so it's gigabits. Now NVLink 3, so this has this much amount of bandwidth. Now for 800 kinds of systems, InfiniBand supports 100 gigabits max per port. So this has like 8 ports, eight wires again going connecting one node to another, which has an effective bandwidth of around 400 gigabytes per second, and so on. So like when you go from one generation to another, this communication bottleneck, the GPU providers or the whole system providers try to reduce this communication bottleneck by increasing the available bandwidth to these nodes. Yeah. So this is a summary slide just to give you a broad idea of like what are the different generations for different models. So recently there are like B200s and which are at present being used latest kind of generations, which has 5 NVLinks, NVLink 5th generation, which has 18 links per GPU. Per link bandwidth bidirectional is 100 Gbps, gigabytes per second. This comes out to have a 1.8 terabytes per second for per GPU NVLink bandwidth. And we know like B200 has 8 GPUs in the system, so the overall system aggregate bandwidth comes out to be 14.4 terabytes per second. So this is no bottleneck or no overlap communication happens, because these are like individual the complete system bandwidth comes out to be zero cross communication or zero bottleneck. So this comes out to be an effective bandwidth for the single system DGX B200 system. Similarly, for DGX S200, H100, and A100, we have different system aggregate bandwidth. Now, I'll stop just after this particular 2 slides because we have a demo to see. Now, Nickel, as I mentioned, is a library for inter-GPU communication. We saw like what are the core operations that is handled by Nickel, what are the different topologies, algorithms that goes behind the scenes in the Nickel library to have inter-GPU communication or inter-node communication. And by running NCCL tests, so the point is like, how do you get benefited by learning about all of these? So by running these tests, you can check if your hardware can reach the design performance for the given setting. So let's say if you're going to run your training workload, you can see how much communication is, what is the effective communication that I can get out of the systems. And then that way I'll have a complete estimation if my software part or, the source code is designed to leverage the maximum juice out of the GPUs or my network. So that's the main benefit. And this is how you run the Nickel test. The tutorials are already there on the GitHub. I'll just give you a demo right now. So just to touch upon, we are going to go through this all of these screenshots in the demo itself. But there are like 2 important pieces in this Nickel test. One is the algorithm bandwidth, and the other is the bus bandwidth. So algorithm bandwidth tells you like how much data is being processed per second by the algorithm. For point-to-point operations, this is meaningful and directly reflects throughput. So this is kind of an algorithm bandwidth, and bus bandwidth is needed for collective operations. So that involves multiple GPUs or multiple nodes. So algorithm bandwidth is kind of broadcast kind of operations, but this does not always reflect the true hardware utilization, especially as the number of ranks increases, right? Because as the number of ranks increases, there will be some latency in processing the data, the network latency, and so on. So the theoretical peak for collective operations depends on both the hardware and the number of ranks that are participating. So bus bandwidth actually adjusts the algorithm bandwidth to reflect the true hardware, actual hardware bottleneck, whether it's in the NVLink or whether it's a PCI or a network, making it possible to compare results regardless of the ranks. So that's the benefit of having these 2 things. Algorithm bandwidth gives you a theoretical peak, and bus bandwidth gives you the actual peak. Yeah. So now we are going to go through a demo for the NCCL. Let me share my screen again with you. Yeah, I hope you can see my terminal, right? I'm not able to see the chat, so if someone can speak, that will be great.
Please increase the font a little.
Okay, okay, okay. Is this better? Yeah. So this is
Yes.
this is my one server, which has 40 GB GPU RAM. This is 800 GPU servers, which has SXM4 backbone. These are like not PCI, so these are NVLink connected A100s. Now, if I do this NVLink NVIDIA SMI topo minus M, I'll get to know what are the different set of number of NVLinks connecting from one GPU to another. So yeah, so here you see GPU 0 is connected to GPU 1 by 12 NVLinks. So we know that A100 has NVLink generation 3. Each NVLink has an effective bandwidth of 25 Gbps, gigabytes per second, bidirectional. So 12 into 25 would be 300 Gbps. So one GPU can communicate to another GPU by the total actual available bandwidth of 300 gigabytes per second. Okay. And now if you see GPU 0 is connected to NIC 0 by PXB. So PXB reflects the PCIe basically through the PCI interconnect. And we saw like PCIe has a, through PCI bridges, PCI has a much lesser available bandwidth than the NVLinks. So, and these are like NICs, each NIC is now connected through another NIC using Mellanox, which is over InfiniBand. Now, if you are going to run the nickel test, this is the command that you are going to run. This differs by system to system because you have different ways of running MPI run. Either you can run it on through MPI, or if you don't have access to MPI, you can run through Slurm. So in the GitHub, I have provided both the ways to run this nickel test. So now the key thing to note here is I have set NP, that is number of processes, at 16. So now I have access to two nodes here. So 8 plus 8 equal to 16. So now I am going to run this all reduced test across two nodes. Okay. And now my the smallest packet size is 1 gigabyte. So right, if you are going to communicate with smaller and smaller packet sizes, you may not be able to utilize the full bandwidth, right? Because you need to have a larger packet size to ensure that your complete bandwidth is utilized. So if you are running with smaller bandwidth, you are going to get a lesser bus bandwidth result. And my end packet size is 8 gigabytes, and I'm going to increase this by the factor of 2. So if I'm going to run this particular command, you will see like for each packet size, how much is the effective bandwidth you're getting. Yeah. So now it is going to run on all these 16 ranks, which are two nodes. So this is one node SCN64. This is another node SCN63. So you see like this is 1 gigabyte packet, and it took it has the overall bus bandwidth of around 133 gigabytes per second. So the average bandwidth, bus bandwidth, comes out to be 136.191, around like that. So like how do you compare whether this particular bus bandwidth is reflecting the theoretical bandwidth or not? So as I mentioned, you look at the topo minus M. You look at the topo minus M output, see like how many NVLinks are connecting from one GPU to another. You find out like what is the effective bandwidth of one NVLink for this particular generation from the internet. You can see the data sheet of A100, and you can find out like or data sheet of NVLink and find out like what is the effective speed, and see like what is the maximum theoretical speed that you can get. And then you try to compare like if you are able to achieve like 80 to 75 to 80% of the actual bandwidth during these nickel tests, then you're good to go. So let's say now I have run this in the 16 or 2 node setup. Now if I'm going to run within a GPU, within a node, that is 8 GPU setup, I'm going to receive a higher bandwidth. So let's say because we saw in topo minus M, we have 25 into 12, that is 300 gigabytes max bandwidth. Now for these two nodes, we are connected by InfiniBand, and InfiniBand, we have a bottleneck of the bandwidth of InfiniBand, that is a bottleneck. So we have around like 200 gigabytes. We saw in this in the slides, right? We have 8 connections from one node to another through 200 gigabit per second InfiniBand network. So that's why we are going to get a theoretical 200 gigabytes. So this is internode. And now let's see what do we get in intranode. So in intranode, we get around like 229 gigabytes per second as the effective bus bandwidth. And this comes out to be in the range of like, 70, between 75 to 80 or 70 to 80% of the actual theoretical possible bandwidth, because 12 NVLink connections, 12 into 25, 300. Right? So this is one demonstration that I just wanted to share with you. What are the different aspects in terms of packet size? So if you are going to increase your packet size, let's say, if I'm going to increase my packet size from 1 GB to 2 GB, what is the bandwidth increment that I get here? We'll just see that. Yeah, we don't see much improvement. This is like, so if you, change some few of the flags here, you optimize few of the flags here, you may be able to achieve, better performance as well. Yeah. I'll slow down a bit. So I'm going back to the presentation now. Yeah. Yeah. So this is about NCCL. One time, maybe 15 minutes. Okay. So now we talked about communication, computation, and the real world performance. So MLPerf is one of the benchmark that provide understanding or benchmarks for different training and inference for different hardware, software, and services. So like different companies, I'll just go to that. So different companies like NVIDIA, Supermicro, Google, and there are a lot of them that takes these hardware, run these benchmarks, which are standardized across by this MLPerf team, and then they are going to report their throughput in terms of tokens, samples per second, or queries per second for both the training and inference. So this gives you an idea of like if what are the standard benchmarks that I need to be achieved when I'm going to get my hardware. So this is the effective hardware part, effective performance that we are going to get using these benchmarks. So Nickel gives you a communication side of the view side. This MLPerf gives you the effective training and inference performance of your hardware. And this has both like multiple nodes, single nodes, and so on. So now MLPerf is again a foundation which creates these standards of training and inference for running these training and inference workloads for different models, different algorithms, and so on. So these benchmarks performance are reported on this link. You can just go through that and do that. And I have in the GitHub, I have also given a complete tutorial, step-by-step tutorial, like how can you replicate these inference results for version 5.0. So version 5.0 has both B200s and I think version 4.0 has H100s. So you can go through that and look at like what is the performance. So for running the NVIDIA reported benchmarks on DGX systems, we need like TRT LLM. So TRT LLM is a library, open source library that generates the optimized model checkpoint for the given checkpoint. Let's say if the given checkpoint is Hugging Face or a PyTorch checkpoint, then it is TRT LLM optimizes that that by doing different hardware-based optimizations to generate a different checkpoint. We call it TRT engine checkpoint, TensorRT. So we need this is the only requirement to generate these benchmarks. So once you have this TRT LLM setup, you can run these benchmarks for NVIDIA, for replicating these NVIDIA reported benchmarks. So as I mentioned, this is replicated across like different modalities, vision, speech, language, image generation, and so on. So there are like different ways of reproducing these benchmarks. So yeah, you can go through this site and you can go to the GitHub as well and see like how to do that. Yeah. Now we are going to the third part, which is computation. So what is the effective theoretical computation, highest compute assessment of my underlying hardware? HPL stands for High Performance LinPack. It's again a benchmarking tool which is used to evaluate the floating point computational performance of the system. So we do it in like 64-bit, 32-bit, or now for deep learning kind of system, it also reports the mixed precision performance of the system as well. So it is HPL is a part of a LinPack benchmark suite, which is widely used in scientific and engineering communities to assess the performance of supercomputers, and parallel computing systems. Now the goal is to measure the system's rate of execution of 64-bit floating point operation, and this is measured in flops. And let's go into a bit technical detail, like how does it do that? So HPL tests the system's ability to solve a set of linear equations using Gaussian elimination method. So in engineering or 11, 12, we saw like if you are going to solve a system of equation like Ax equal to B, if you need to find out if A is a large square matrix, X is the solution vector that we need to identify, and B is the right-hand side vector, then we do it using kind of value decomposition or Gaussian elimination. We decompose the A matrix, which is a very big matrix, into a product of lower triangular matrix or a upper triangular matrix. Right. So lower triangular matrix, like all the values above my diagonal are going to be 0. Upper triangular is like all the values below my diagonal is going to be 0. So the benefit of this is like you can split your large square matrix A into multiple splits and these splits can do a parallel operation, do the operation parallelly within within a GPU. So you don't need, this is not a sequential operation, this is a parallel operation, right? So this particular HPL utilizes like various standards like factorization, nickel communication, matrix multiplication, and so on, and use these libraries to find out like what is the effective performance that you can get, computation teraflops that you can get out of this this hardware, underlying hardware. Now this is how the output will come to you once you run this HPL system. So one is P. So P is basically the number of processes to distribute the row blocks over. Q is number of processes to distribute the column blocks over. So like if you see multiply P into Q, so this comes out to be 8. So when I run this particular process, I used 8 GPUs, and when I run this particular process, I used only 1 GPU. So here, if you see, these P and Q is basically a split that is going to go into different GPUs for processing. Again, if you know the LU decomposition to solve this linear equation method, you can understand like how does it do it by doing these parallel operations, try to decompose each submatrix into different parts, and then going to arrive at a solution by aggregating them at the later point of time. So you see the square matrix is of size 264,000. Why this? Because this is the max size that I can occupy the whole 80 GB RAM on my system. Right. So this is my global matrix size, and this NB is my block size. So there are like these number of blocks that are used when dividing the larger matrix into smaller chunks of processing. So now this gives me an effective bandwidth of like 368 teraflops, which comes out to be 46 teraflops per GPU when I run this 8 GPU system, when I run this benchmark on 8 GPU system, and I got this 47 teraflops for a single GPU system. So now the question again comes, how do you compare this performance? So when we saw about nickel, we saw like we can use data sheets to compare the performance of my the effective throughput and the actual throughput, the theoretical actual throughput. And for MLPerf also, we saw like how do we compare the performance. For HPL also, we can compare the performance by looking at the data sheets. So this was again with the A100s. The earlier systems were with H100. So you can see like the performance difference, computation performance difference that you will receive when you go from A100s to H100s. And now with B200s, you will get a higher jump, even more around like 1.8 times than H100s. So like that's why these different GPU models try to market themselves as like both from the communication and computation side. For A100s, you get around like 14 teraflops and 17 teraflops with the same GPU RAM. So now coming to the back to the point, like how do you compare whether your performance is up to the mark or not? So you look at the data sheet of each of the GPU model. So if you search over Google, like give me H100 data sheet, it will give you NVIDIA hosted PDF to compare against. So here you see like H100 SXM, you will get a max FP64 performance of 34 teraflops. FP64 tensor core is 67. So now in this slide, we saw that we get around like 46 teraflops highest performance. And this can be improved. Like if you change the number of blocks from 1024 to, let's say, a number of them, you might get a larger, teraflop performance as well. So these can be again optimized, but it just this whole set of slides are just to give you an idea like how much you can expect from the GPU. And when you're going to run your actual workloads, how much you're going to receive. So there is no discrepancy between like you are going to receive like 30% performance from with respect to the actual throughput. So that won't happen, and you will be in control of how the things are going when you're going to train or infer run the inference workloads. And again, FP64 tensor core for 800 we saw like 19.5, and here we see like around 17.21, which is decent enough with respect to the actual theoretical throughput. Yeah. So at last, in summary, I hope we are on time. Yeah. So we covered three things. One is nickel test, which is used for analyzing intercommunication within the particular server, among GPUs, and among multiple nodes, among multiple servers. This is essential because distributed training happens through communication through these channels. So we know like in between two nodes, we have an InfiniBand or an Ethernet that is connecting, which could be a bottleneck, because inside the particular node, we have a high bandwidth, like we saw 1.8 terabytes per second bandwidth is available for the GPU to 0 to communicate to GPU 1. For MLPerf, which is an industry standard benchmarks for benchmarking machine learning workloads, both for training and inference. You can evaluate like whether if you're running a particular set of piece of code which is not particularly optimized, then you can compare with the MLPerf model and see like how much you are getting with the standard set of hyperparameters or configurations. And again, HPL, we saw like it assesses the computing power of the clusters, and it validates like overall system performance for HPC kind of tasks. Yeah. So I think this is all I have for the time being. I'll just take you to this particular repository, and we may pause for questions. Yeah. So this is the repository that I've created. So if you go to this folder, you'll see like for different NCCL, HPL, and MLPerf, you have a markdown files. So this gives you like idea about like NCCL, what is NCCL, basic understanding, and the setup instructions. So the setup instructions are both using this Slurm and through MPI run. Yeah, using MPI run. So yeah, both of them are there. And you can also like comment, post issue on the repository and ask like if you are stuck anywhere. And similarly for HPC, there is for using Slurm. And yeah, you can tune the benchmark. So all the things that are presented here in the slides are here in this. Yeah. Similarly for MLPerf benchmark use on V200s, I have pasted how to reproduce it step by step. So yeah, you can ask the questions like if you're not able to get the answer on the actual library, you can post it and I'll try to answer as well. I think that is it from my side. You can post your questions in the chat box. Let me know. The feedback like do you want any improvement for the next sessions, and yeah, so let's share the data link. Yeah. So one question is there, how to set up the MLPerf benchmark. So I've pasted the instructions, uh, put the instructions in the GitHub. So you can go over it. There is like, you can refer to the MLPerf GitHub repository as well to do a step-by-step setup, and you can refer to that as well. So both of the things are there. Yeah, I've pasted the GitHub link. I'll paste it again. One question is like, in LLM building from scratch, what kind of use cases are we going to build? So one is like, we are going to cover both from the conceptual and the broader point of view. When you are going, how do you develop LLM from scratch? So this is more from the pre-training point of view, the second and third session. So second session, like data curation, may be applicable for fine-tuning part as well, because once you have raw data with you, you need to clean the data to ensure that it aligns or it fits to be understood by LLM, right? But third session is mostly from the how do you do this distributed large-scale training. So this is basically like more from the pre-training point of view. Not so in the later sessions, like probably fine-tuning sessions, and maybe we can add new sessions as well to cover different use cases as well. Yeah, post-training optimizations, yes, we are going to cover in the fourth session. I've added the slides in the GitHub. Yeah, you can go through that. So yeah, RL part we are going to cover in the fourth part of it. So second is again data curation session. Third is pre-training, pre-training part, distributed training. And fourth will be the post-training part. Fifth will be deployment. Uh, yeah, yeah. Can I simulate nickel on NVIDIA GPUs connected through? Yeah, simulate, I'm not sure. How can I simulate it? Um, yeah, I don't have answer to this for simulation. Sorry. Can you provide the best method to do the deployment of LLM? Yeah, so there are different ways to do that. So one is the LLM library that helps you in optimizing the trained model for the underlying GPU, and the other is TensorRT library that can help you uh, in optimizing the model for the best inference throughput. How can we make an LLM model parallelize and then make it a perfect inference engine? Yeah, so that's what we are going to cover in these sessions. How can you train the model in a parallel setup, distributed setup? And then in the later part, we are going to see like how can you optimize this for the best throughput and the best latency. Which high-level libraries are we going to use for training LLM? Yeah, so we are going to use Nemo library, which is based on Megatron Deep Speed. Sorry, on Megatron, not on Deep Speed. Deep Speed is again a fork of Megatron. So we are going to use Nemo to for training the LLMs. So why Nemo particularly? Because it has easy to use interface, and the features exceed far more that are available in the deep speed forks of Megatron. Yeah, HPL is a system-specific benchmarking tool. Which tool can I use for application-specific? Yeah, that's a interesting question. So by application-specific benchmarking, I think you are referring to, let's say, if you develop a particular application, deep learning application, how can you benchmark this? So there are different methods, different libraries that are already available in open source. So one is GenAI Perf library. So I'll just paste type the name. So this GenAI Perf gives you replicates the pre-trained models that are already there in the market, and you can run these benchmarks and see like how much performance you are getting on your hardware. And then MLPerf is again you can do that for the application specific benchmarking, because MLPerf gives you for different modalities. Like for image, you have a stable diffusion, so how much performance you are getting through stable diffusion. For text, they provide benchmarks for Llama and so on. And for audio, they also provide some benchmarks. So you can get through these application specific benchmarks, like how much you are getting on your underlying hardware. Will offloading be also covered? I'm not sure, like, what do you mean by offloading? If you can expand it again a bit. Can you provide a little bit more about MLPerf? Yeah, it is available in the repo. So MLPerf deployment guide for B200s are there in the repo that I could replicate on the hardware that was available to me. Yeah. So you can also, so there is complete documentation for other hardwares as well. So you can go through the MLPerf library and see like how can you do that. Yeah, so which high level libraries for training LLM? Yeah, as I mentioned, we are going to use Nemo. Okay. So we are going to use Nemo library, Nemo framework, which is again based on Megatron. I'll paste the link itself. Give me a second. Yeah, this is what we are going to use during training. Is okay, offloading models to CPU and RAM with GPU. Okay, that's an interesting part. I think we can get it covered if we have time, and we can create a new session for the offloading itself to see like how can we offload models to CPU. Yeah, we can see that. I think I'll have a look at it again. So will you be covering VLLM for deployment? Yes. So both VLLM and TensorRT we are going to cover for deployment. TensorRT. Yeah, I'm going to cover that. So is MLPerf used to find bottleneck of a hardware like NICs? In my experience, I'll suggest like Nickel is the best way to find out the bottleneck because it will give you raw communication performance because MLPerf is more from the application point of view. Yeah, MLPerf is more from the application point of view. It will not give you a clear idea of like what is performing what. Nickel gives you more, it's better performance idea. LLM, yeah, I have pasted the LLM training library again. Can we guide on training Indic tokenizer embedded in LLMs? It is little different than English LLMs. Yeah, that's an interesting point, Jaideep. See, the underlying algorithm for tokenizer is still byte pair encoding for Indic as well. Now, this is not very perfect for Indic because in English, when we are going to use this BP tokenizer, it's again a statistical based tokenizer. It find out the tokens based on the frequency of occurrence throughout the corpus or throughout the corpus that you have given for training the tokenizer. For Indic, we may try to come up with a new tokenizer, but again, this is BP is the most prevalent algorithm for tokenizing even the Indic languages. But there could be different ways to tokenize because Indic is a different. All Indic languages have like similar way of creating a sentence. So like English has the formulating a sentence, you need to have initially a subject, then verb and object. So it's subject, verb, object kind of formulating a sentence. For all Indic languages, it is subject, object and verb, right? मैं खाना खाता हूँ, मैं बोलता हूँ, मैं बाहर जा रहा हूँ, right? In English, you will be the I am going outside. So it's subject, verb, object. So now, in addition to this sentence construction, Indic language has a specific way of pratyay and upsarg across all languages. Most of the Indic languages are have a similar structure. So most of the Indic languages are derived from having some Sanskrit vocabulary within all these languages, and they have a concept of upsarg, pratyay, karak, and all these different variants. So this is different. So we should not deal it in the same statistical way, the way English tokenizer are dealt with. But yeah, that's a more prevalent way. So we are probably going to cover this since you bring up this topic. I'll make a note and going to cover this tokenizer part as well. Yeah, thanks for that point. Maybe in the next session itself, we are going to cover this tokenizer itself, like how does the different algorithms like unigram based algorithms or BP based byte pair encoding based algorithms are used to create these tokens, which are the basic units for training these LLMs. I think Pankaj, we do not have any more questions.
So if we do not have further questions, we can close the session for today. For next session, we will be intimating you via email and we'll share the link. If you have any questions that have not been posted over here, you can drop us an email at npsf-outreach@cdac.in, and we would collect them and get the answers from NVIDIA and would post back it to you. So thank you everyone for joining the session, and we are closing the session.
Thank you, everyone.